various kinds of noise, and yes, this morning, and we discussed that there are noises of variety kinds, short noise, Johnson noise, then there are GR noise, and of course one of the noise I said I will talk about is popcorn noise, and of course finally we will derive some expression for KT by C noise. Okay. So these are some noises of interest. The first among them is called short noise. This noise occurs due to quantum nature of electron flow through a potential barrier like a PN junction or a metal semiconductor junctions. The carriers actually exhibit average rate, which is average means DC, of crossing the barrier, but individual carriers can have random motion. So on average there may be number crossing the barrier, but in individual ones will have different probability of crossing. Okay. In above equation, the short noise equation, which is IN is the current noise source, is 2QID delta F, and in the above equation ID is the forward current of the device, which barrier about which you are talking about, and delta F is the bandwidth of noise measurement. One can see from the expression that the short noise is related to the forward current by root of ID, but there is no term which is KT temperature dependent, and therefore short noise is normally temperature normally, and I will someday show you that it is also to some extent function of temperature, but very small dependency. In MOSFET, particularly where you are worried about MOSFET noise, one of the short noise is seen not in saturated MOS transistor, but more so in the sub-threshold region where current is e to the power QV by KT kinds, and there MOSFET do show some kind of a short noise. Otherwise most of the time MOSFET do not show any short noise. So the first noise in the list which I said is the short noise, and I repeat, it is essentially randomness in carrier motion across a barrier, though on average there is a DC value available. Okay. The short noise, as I say, is dominant only in many of the bipolar devices. Why? Because there is also the dependencies e to the power QV by KT. So any relation GM is like QIC by KT. In the case of sub-threshold current, GM is again QID by KT. So wherever the GM is only a function of I and temperature, those cases short noise is observed. Okay. Otherwise short noise is not seen in a normal MOSFET operations, neither in linear nor in saturation. The second noise of interest is the Johnson noise, which is very popularly known as thermal noise, and any random carrier motion may be due to the drift, diffusion. You get the RMS noise power, and that can be expressed as the noise spectral power is SNF, which is taken from a frequency of F1 to F2, KT is the thermal energy, and then it gives you a spectral density of KT into delta F. And obviously since the SNF is proportional to T, this is thermally dependent noise. So larger the temperature, larger is the noise component. Typically, for example, if you are looking for a resistor where random motion of carriers constitutes that is mobility fluctuations or variations, carriers move through by drift or diffusion, then we can see this can be modeled as a noiseless resistor, and in series to it there is a noise source which is related to the resistor noise. Okay. Now the spectral density, it can be also written as Vn square by R, which is KT delta F, and if I connect it is Vn square KTR into delta F, where Vn is the noise voltage, and if it is expressed in RMS and per hertz, if you calculate, then the noise voltage Johnson noise or thermal noise is expressed as 4 KTR. Okay. So now you can see from here the noise voltage of a resistor is a function of temperature and function of the resistor value itself. If I see a Vn square, and if Vn square is something to do with the resistor, what is the current in this? Ion square will be Vn square by R square. Vn by R is the current, so ion average noise current is essentially equal to square of that is Vn square by R square, and that is called current noise source. So why I am showing you this is Thevenin's equivalent, the other could be Norton's equivalent. The current noise therefore is ion square, it is actually ion square bar, slightly long, square नीचे होता है और bar average value of that. So which is Vn square by R square, and if I replace Vn square then I get 4 kT by R or 4 kT into G, where G is the conductance which is 1 by R. So I can replace a voltage source, noise source by current noise source by multiplying it by relative whatever resistance I see through which this current noise current flows. Okay. Why I am looking into this term, in the MOS transistor what is the thing flowing through? The IDS. So a current is flowing through there, so I would like to replace noise current sources there rather than voltage current sources, except at the input source where I may use Vn square terms actually. The next noise of interest is called 1 upon F noise, or also called popularly flicker noise. Okay. This also is a very popular name. Whatever statement I have written here, I may preface it with saying all these are strong conjectures. There is no real proof to prove that the following things actually relate to 1 upon F, okay, and therefore interesting because no one actually proves it that is correct, okay. So with any other thing also I can prove it is 1 by F, okay, therefore take it little pinch of salt, but that is what most people agree that this is what it may be. And it is, as I said, this noise was also invented in 1923 by Mr. Johnson, okay. Particularly he was working on vacuum tubes, there were no semiconductor device then, okay. What he says, or what is the statement made, is due to number of fluctuations occurring due to defects, contaminants and interface state density, one observes 1 upon F noise. In the case of MOS transistor, the silicon and silicon dioxide or any other insulator has an interface which is between insulator and semiconductor, and the current transport is at the surface of this interface, is that correct? Between source and drain you have an interface where the carriers are actually moving, okay. So any change in the interface density will change the what is called relaxation time associated with this, and since there is a time associated with recombinations there, surface recombinations, variation there leads to a noise component, and this noise is found to be inversely proportional to frequency. So larger the frequency, smaller is the output. If you really plot 1 upon F noise, okay, I call it 1 upon F noise versus F, it is something like this. It actually exponentially goes down, but in real life this, because I say some show if you are only taking interface, it actually goes like this. So there is no reason to believe that it follows exactly 1 upon F noise linearly. The exponential is such this that it also closes near to the linear side. So it is somewhere one does not know which is the real cause. Any fluctuation, there can be a mobility fluctuation, there can be density fluctuation, carriers can number may change, okay. So any defect, contaminant or interface states can lead to 1 upon F noise, and therefore in MOS transistor in specific 2 noises of interest to us. One of course is the thermal noise, because there is a, why thermal noise? Because transistor essentially is a voltage controlled resistor. Since it is a resistor, it shows thermal noise, and the other noise possibly because of the phenomena of interface state in specific, it will show 1 upon F noise. Okay, so exact nature as I say is unknown. There are almost people say, there is a professor, of course he is no more now, he was at University of Minnesota, his name is Eldert van der Ziel. There is a book on noise phenomena in materials or semiconductors, 600 odd pages only on noise. Okay. Any device you create, anything you say, next few months this old man will work and actually find noise for that new one. Okay. So that is what van der Zeel was called Mr. Noise. Okay, and why I know him so much, because my PhD guide worked under him at Minnesota. So that is why he is my grand guide. Okay. So I must make some noise for him. Okay. Of course he was not one, there is another vendor, Van Vliet was also the other guide, but van der Zeel was one of the two guides he had. Okay, so 1 upon F noise is going to stick there irrespective because of the MOS. So you find in a bipolar this noise is not as dominant as in the case of MOSFET. The 1 upon F noise comes in the bipolar in the base transport only, because there is a fluctuation in base, but that is comparatively much weaker in amplitudes compared to MOS 1 upon F noises. Okay. So if you are looking for MOS circuits, you do not neglect 1 upon F noise. If you are using bipolars, then do not lose short noise, because that is not here in the case of MOSFET. Okay. Is that okay? So the next of course is generation recombination noise. In any semiconductor or devices, there is a statistical variation of numbers as they move, because all the transport phenomena is basically random motion. Okay. Diffusion for example, it is a random event. So any statistical number variation which has a variance available with it, this leads to a noise which is popularly known in the literature as random telegraph noise. Okay. Why this word came, can you anyone suggest? Why this name was GR noise was earlier called RTN? I do not know whether, yeah he knows. When the earlier times when the you were sending messages, okay, Morse code, so there was a switch which did dot A, something code we made, and tack 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 tack. So every time switch was this. So depending on the pressure he puts, it could change the actual letter which it will be received the other end. Okay. So it was, therefore it was called that it is fluctuation numbers, statistical numbers, therefore it was given a name telegraph noise. One of the method of measuring the interface states or rather variation is what is called as post office noise measurements, which actually measures RTNs. Okay. जो मास फिजिक्स में काम करना चाहते हैं थोड़ा ये पोस्ट ऑफिस नॉइज मेजरमेंट पढ़िए. ओके. मास फिजिक्स यानी प्रोफेसर वासी या इनके साथ जो फंडा ही मारना चाहते हैं वो जरूर पढ़ें कि ये भी एक नॉइज वहाँ तकलीफ दे सकता है तो एडवांटेज भी देता है. यू कैन मेक यूज एज ए मेजरमेंट सिस्टम. The last noise, in your second year if you would have asked me, I would have explained it much more there, because this is more device theory, interesting theory. Okay. The last noise of interest, which is also very popular in communications, is called burst noise, and as I said it looks like a corn when bumps out, so it is called popcorns. Okay, so it is called popcorn noise. And in a MOSFET channel currents, because of the switching signals going through, there is a burst noise available, and this burst noise is essentially called popcorn noise. Okay, it's essentially because of the modulation of channel currents, because when you switch. Okay, you can see when this happens, there are two phenomena of what we call capture and emissions of the carriers, and depending on their emission time constants and capture rates, the cross section of the capture where it is going to capture because of defects including interface states, they show some kind of fluctuations, and these are found to be 1 upon f square kind. Therefore they was called a popcorn noise. Okay, it pops up. Okay. So these are some noise, there are a few more but some other day. These are relevant for us, so I thought at least I should talk about our requirements. But in design we don't damn care about so much about popcorns because they are one upon us, I mean they die down very fast. Okay, so we say that most region of interest, this may not be of that relevant, but it is not so true that it is not relevant, it is. So let us look to the noise due to components. I will come back and say all same thing which I started with noise as a theory. Two things of interest to me, this noise due to components, a statement which I could have made earlier but I now want to make. There are two types of noise we worry about. One of course is man-made noise, okay. We are most famous for it, okay. That is signal coupling or substrate coupling in the mixed signal or finite PSRRs. These are essentially called man-made noise, okay, due to the system you create. And possible methods of elimination, this morning I already said fully differential system probably can help, and one of the method of reducing this man-made noise is to properly lay out the circuits. Since we have not done layout so far, when I will do layout, I will give a name of layout method, is called common centroid method, okay. So we will come back to layout and discuss it, why common centroids, okay, and at that time I would say yeah, this layout taking care helps you to reduce noise in particular, and this is very important in real logic, real implementation of layouts on chips, okay. So this is relevant. Of course if you do this and properly do this, you can contain noise to a great extent. Okay. The other one which is not really so called, I call it man-made, not due to the system I am making, is essentially electronic noise due to devices, which is inherent with the way we work on that, okay. So this we already somewhere discussed, okay. Now we will, this we haven't discussed very much, but signal, the substrate coupling I will talk to you later. Maybe I can show right here what essentially substrate noise is about. You have an n-channel device, let us say sitting here in a substrate, and this area is for analog. This whole area is digital, this is analog area. Please remember, any such circuit here will be constantly connected to this substrate through digital means, capacitive coupling, is that clear? Switch, you do 1 0 1 0, so this substrate also gets 1 zeros on that, but that this analog area is sitting on the same substrate which may have equivalent of resistance, sometime capacitance. So this change here is essentially getting transferred to analog irrespective whether you want it or you do not want it. This is called substrate noise coupling, okay. This, because of the digital part, your analog parts keep receiving switch noises, okay, and that is something which is relevant in all mixed signal design. So one method is you put it too far away so that it dies down. However, too far away is the problem, that means you will not do anything, that area is wasted. Or to reduce some kind of, you put a guard ring, as we shall see later, to protect it from the actual gain occurring there, okay, can dam down by something. So there are ways of reducing substrate couplings, but there is always will be a substrate coupling any mixed signal chip, okay. It can be minimized but cannot be made 0, okay. So this analog sitting in digital is the major cause. Please remember, analog does not inject as much noise because it's DC, it's some kind of a constant value, averaging thing. This is running at now gigahertz on off, okay, and that creates hell of coupling noise to the other analog parts, okay, and that particularly PSRR is the one which is heard maximum because of if op-amp is being used here, okay, and in turn therefore even CMRR gets heard, okay, variations. So these issues which I thought are not irrelevant, so I must say that yeah, substrate coupling is taken care in actual designs. Signal coupling, do not bring lines closer because they may have common capacitive coupling, okay. It is called mutual, two lines. There is a capacitance to the substrate, but there is a capacitance lateral between the two metal lines which are sitting on insulator, oxide. So two metal lines sitting on oxide may couple themselves, okay, which is the cause of signal couplings, crosstalks as I said. And there is, because of the noise, the maximum allowed power supply rejection may get exceeded because the noise may override that, okay. So these are called man-made. Okay, so let us look for electronic noise. So the other noise are relevant. I already said the electronic noise in devices and circuits, minimum detectable process signal is limited because of the noise. Noise directly shows trade off between power dissipation and speed, and now this is the result why I actually brought this sheet here, why we are worried, okay. Low noise requirements dictates the use of large capacitors, okay. Larger the capacitor, KT by C noise is minimum, okay, and or large GM, okay. Both leads to high power dissipations. In digital, C dV by dt, dynamic power. In analog, GM by C is itself creating large powers, okay. With scale down technology, the power supply voltage also decreases, thus reducing the SNRs, okay. Hence design of a low power, low voltage and or precision circuit has a strong dependence on electronic noise. And current era, we have worked mostly in 0.18, 0.25 micron processes, though they are short channel but not so short. You will be working on 65, 45, 32, 22, 16, 11, 9, 7, 0. So since if at all you work in devices and circuits, if at all, those who work may find it that this design is now becoming more noise dependent. Earlier the values of the power supply was 5 volt, this is in millivolts, so damn care. Now the noise is actually hundreds of millivolts and your Vt is 200 millivolt, you are very close to where you should not be, okay. And therefore of now noise issues are more relevant in designs as they were not so very relevant in earlier technologies. So most of our designs are where analog we do only on 0.18, 0.25. Some students may be working on 0.13, okay, and some smarter may be working on 90 nanometers, but no one is working on 30 to 28 or 22 nanometer process because we do not have tools, forget about the other, we do not have tools to do that, okay. So this all statement is humbug, okay. Okay, so as I said you that electronic noise is a relevant part now of today and therefore you should pay a lot of attention. Please remember C increase is not very much agreed because that actually changes the bandwidth and it also improves or rather increases the power dissipation. In our op-amp design you must have seen I have already specified our cascade design amplifier, I said this is the maximum power allowed for you to dissipate, okay. So that is the budget, this is called thermal budget. Once you are given this, you cannot exceed that. How do I decide the thermal budget for a chip? I had discussed earlier but just think of it. How do I decide this is the power I will allow you to dissipate? Correct. So there is a issue which is called thermal resistance is actually delta T by delta P. Change in temperature with change in power is called thermal resistance. So from the junction to the substrate down to the heat sink, how much is the thermal resistance I can have which will allow me max, and temperature rise is maximum given to me not more than 125 degree centigrade or not less than minus 55 degree, whichever the range mill standard wants. Within that range for given theta of those layers you are using, there are R1, R2, R3 in series, so like R is equal to rho L by a similar equivalent for thermal you can calculate, find thermal resistance. With this 3 thermal total with what temperature you allow, P is fixed, okay. So once P is fixed, then you know how many vertical lines in your chip will have. So you actually divide now power so much milliamps here, so much milliamps here, so much into V is the power, okay. So that is called allocation. So first thing when you start designing a chip is the power allocation. Where do you allocate the power, okay. So some things even if you can do better, because you say no I cannot put all the power here, I will do some more other things. So many designs, please take it that ये statement ठीक रहता है, but actual में when you do it you will have to do much more thinking how much. So the performance may not be the best, but there is a performance, otherwise there is no performance also, okay. And therefore one has to worry how much power you will be allowed per arm, okay. Like in DFAM, so much microamps current, so much VDD, each arm is so much. So you know you are allocated, the 10,000 DFAMs are going on. Now you calculate how much power I am allocating to them, okay. So the game is to actually know how much is power to be allotted, okay. So please do not think it that I am just talking some muck, it is a very relevant thing, and therefore I must know the thermal issues very clearly because it is decided by the power at hand in some way. Coming to the realities, we like to calculate thermal noise due to resistors, okay. A typical resistor can have either a current source noise or a voltage source noise. If you have you write a current source here, then it is Im square, this is 4 kT by R, amp square per hertz, okay. And now one interesting thing is, if I have two resistors, okay, then if I want to calculate noise due to this, so what I say, this is noiseless resistor shunted by noise current source, another current resistor with its own current source, noise